Hello there again, and welcome to another video. Now this one's a little bit different from my usual videos because in this video I'm actually going to try and do a little bit of a tutorial for the flat earthers out there on the mathematics of a spherical earth, because I've dipped in again at a few of the videos that people are doing on the flat earth, and quite frankly it's a little bit embarrassing. People really don't seem to know how to do the calculations or what they mean by things like drop down, or how much of a hump of a water there should be between locations, and things like how much should be obscured by the horizon. So I'm actually going to just try and help you out a little bit with some mathematics, because I've seen so many of these videos where someone, they'll go to the shoreline and they'll point the camera at something 7 miles away and they'll say, well, the drop down should be, well, it's 7 times 7 times 8, and it's 392 inches, that's just 32 feet it should be, and it doesn't look like 32 feet's been obscured. Well, it wouldn't be, because that's the drop down. That's not how much has been obscured by the earth. Anyway, first of all, I want to talk about the formulas for drop down, because there's actually different ways of defining it. I came up with 4 different ways that I can think of anyway. So I'll just quickly go through what they are. So say this is a spherical earth here, okay, or a sphere anyway. So you're up here, and supposing you imagine a tangent straight from your location, like that, and then going straight from that point to the centre of the sphere. So because that's a tangent, I'll call it that distance t, and we want to know that, say, that calculation there, that distance there. So it's the distance straight towards the centre of the sphere. Well, the formula for that is, now I'm just going to give these without justification. I want to rattle through these quickly. The formula for that one is the square root of r squared plus t squared, take away r, where r is the radius of the sphere, or the earth, if you're talking about in terms of the earth. Now, another one is, if we start there and we go along a tangent, a distance t, now instead of going straight towards the centre of Earth, if I go straight down this time, I won't go quite far along as that. Suppose I go from there and then I go down to that distance there. And so I've gone along a distance t, you're standing on this sphere here, and you want to know that distance there that is vertically down from your location. So you go along there and you go down. Well, what's that going to be? Well, that's going to be r minus the square root of r squared minus t squared, where r is the radius. Okay? And another way of defining it, though, is if you start at a location on the surface of the sphere here, and you follow the curve of the sphere this time. So you're following an arc. So this time you're following a curve there, A. So we'll call it A. And again, suppose you want to know what the drop down is, like this. So you want to know that distance there. So you followed a distance A along the surface of the sphere, and you want to know, say, how much of a vertical structure would be obscured if you were right on the surface of the sphere here. Well, that is given by, well, first of all, if that's the angle x, then the formula for that one is r times, in brackets, 1 over the cosine of that angle x minus 1. And that angle x is given by 180 a divided by pi r. Okay, so that angle there, you get it by doing 180 times the arc length there, divided by pi times the radius. And then if you do 1 over the cosine of that angle minus 1, multiply all of that by the radius, that'll give you what that distance there is. And there's one more. If you follow the arc length a this time, but this time you want, let's see if I can draw this, that distance there. It's the distance that's vertically down, so it kind of corresponds to that one. But instead of calculating according to the tangent distance, you're calculating according to the length you've gone straight along the curve of the sphere. Well, this one is given by, now again, that's angle x, that's r, it's given by r times 1 minus the cosine of x, where x equals 180, I'll try that right neatly, 180 a all over pi r. So those are your 4 formulas for calculating the drop down, depending on how you're defining it, depending on how you're thinking about what it actually means. So there's 4 different concepts of drop down. Now, fortunately, for small values of a or t, when a and t are both small compared to the radius of the sphere or the Earth, all 4 of these give pretty much the same answer, pretty much exactly the same answer. So if a, I'll write this down here. So if a is very small compared to r, if t is very small compared to r, then we can just equate a equal to t equal to a distance d, okay? So if that's in miles, then all 4 of them for small distances approximate to this nice formula here, which is d squared times 8 inches, which is the formula that most of you have learned. Now, I've worked out, I'm not going to go into all the details. I did proper, I expanded all 4 of these into infinite series and showed, and it does turn out that the first term, if you expand them into an infinite series, does work out to be d squared times 8 inches. So this is a nice little rule of thumb for working out the drop down. And like I said, it doesn't matter for small distances, it doesn't matter which one of these 4 drop downs you're thinking, they all pretty much give the same answer. And they all give the answer d squared, where d is in miles, times 8 inches, and that'll give you an answer in inches. So that'll tell you the number of inches for the drop down given the d in miles. So miles squared times 8 inches gives you the answer in 8 inches. Like I said, that'll give you a nice approximation for all 4 of those formula there. Right, so that's your 4 drop down formula. I'll just leave it there so you can pause it and look at that if you want to. The next one I want to look at is this thing I was going on about, which is, I think some of you call it the hump of water or something like this, which is, say you've got two locations on Earth or on the surface of the sphere, and they're a distance apart a. Now I'll call it a because it's going to be an arc length, so I'm talking about the curved length there. Now there's going to be a line straight across through the sphere from there to there, and what we're talking about is that height there. So we're talking about the kind of how high the hump is, as some of you have called it. I'm sure I've heard some of you say these strange things. Now that distance there is given by this formula here, which I'll write down for you. It's given by r times 1 minus the cosine of 90a divided by pi r, those brackets. So you do r, the radius of the sphere or the Earth, in brackets, 1 minus the cosine of 90 times that length there, a, divided by pi r, and that'll give you that distance there. Now that's a horrible looking formula, and that one also simplifies to a nice neat little rule of thumb that works for small distances. It'll give you a good answer even up to about 100 miles, which is d squared in miles, distance between the 2 things in miles, times, now not 8 inches, it's times 2 inches. Right? So that's your nice little simple rule of thumb for this one. D squared in miles times 8 inches, and that'll give you the answer in inches. So for example, if you had if you had a bridge that was 10 miles long, like this, so the bridge is 10 miles long, and you want to know how far does it go up in the middle before it comes back down again if you're thinking of it as a curve. Well, easy enough. All you've got to do is you do 10 squared times 2, so that gives you 100 times 2, it gives you 200 inches. Okay, so that's just a nice little simple rule of thumb that tells you the answer for how far something should kind of go up if it's a bridge or something like this, or a hump of water or whatever it is you're thinking about, right? So that tells you how much of a hump you get. Now the last thing I want to look at, and this is the thing that you all get really confused about, which is if you're standing on the surface of a sphere and you're looking at something in the distance, how much of it should be obscured by the curvature. Now what all of you do is you all calculate the drop down, which is not going to be the same as how much is obscured by the curvature. That would only be true if your head was right on the ground, but it's not. So let me do a slightly exaggerated drawing. Suppose you want to know, say you're here. Okay, let me zoom in on that for you. Say you're here, and you want to know how much of a vertical structure this distance away is along here. It's going to be obscured. Now, if you do the drop down, now depending on which version you're using, it doesn't matter, but then what you're calculating is that there. But that's not how much is obscured by the horizon, because your eyes aren't right on it. So even now, this is one of the things that people don't get about the geometry of a sphere. You only have to go up a small amount, and the amount that's obscured drops down quite dramatically. So if your eyes are right on the surface, all of this is obscured. You only go up a little bit, and look how much less is obscured. It's actually quite dramatic. So on the surface of a sphere with radius r, if your eyes are at height h above the sphere, and you want to know how much of something in the distance would be obscured, it's not the drop down. The drop down would be the distance squared times 8 inches. Now, I messed around and I thought, can I get a nice little formula that tells you how much should be obscured by the curvature of the Earth? If it's a distance d away and your eyes are in height h above the surface. Well, I got it down to this, and I'm going to show you this formula. It's 8d squared. Now that's your drop down. That's 8 inches times the distance squared. But you have to add an extra couple of terms on. Now don't worry about where I got this from. It does work, I can assure you. Do 5.657 square root of h d plus h. Yeah, it's a relatively simple formula. Now I'll just make this clear. D is the distance that something is away from you, and that's in miles. H for this formula is the height that your eyes are above the ground, so like there, and that's going to be in inches. And the answer that this formula gives you is in inches. Now, it only gives you meaningful answers if the thing is past the horizon line. If you calculate it for something before the horizon, all you're doing is calculating the distance from this line to the sphere, or the surface of the sphere, or the surface of the Earth. So it only really tells you if something's obscured if it's actually past the horizon line. So you've got to make sure that the thing's actually past the horizon line already. And I've gone into how to do that in other videos. So this is your formula for calculating how much something should be obscured by the curvature of the Earth. 8d squared minus 5.657. Now don't worry about this constant here. Don't worry about where I got it from. Times the square root of the height times the distance plus the height. Now let's look at let's look at this formula in action. So supposing supposing you want to calculate how much something obscured if it's, say, let's say it's 7 miles away. Okay. Now, if your eyes are right on the ground, the height of your eyes are 0, then the amount that's obscured is just the drop down. So it's just going to be 8 times 7 squared. Because the rest of the formula's got h in it, so if h is 0, they just disappear. So it's 8 times 7 squared, which is 392 inches, divided by 12, so that gives you 32 feet. 32.7 feet. So that's the drop down over 7 miles. Now if it's 7 miles, and say your eyes are so a minute, this is for 0 inches. I'll write that in there. So say if this is your height above the surface of the sphere, so your head's right on the ground. So the amount that's obscured in the distance is just the drop down. Now say your eyes are, say, I don't know, say 6 feet above ground. Now that's 6 times 12. That's 72 inches. So that gives you, remember our formula is 8d squared minus 5.657 root h d plus h. So that gives you 8 times, now d is 7 squared minus 5.657 square root of 72, remember it's in inches, times 7 times the distance plus 72, which gives you 8 times 7 squared minus 5.657 times the square root of 72 times 7 plus 72, which gives you 128 inches, which is divided by 12, 10.7 feet. Now notice something quite dramatic about this, okay? Notice something here, because your head's right on the ground, then something 7 miles away, the bottom 32 feet will be obscured, 33 feet. You only go 72 inches above the ground, 6 feet, and only less than 11 feet of it is obscured. So you can see that just going up off the ground makes a significant difference to how much is obscured by the curvature of the earth. So suppose you go, let's just do one more, suppose it was, suppose you went up 20 feet, so 20 times 12, so that's 240 inches. And it says 6 to 7 miles. Then I'll just do the calculation quickly. It's so it's 8 times 7 squared minus 5.657 square root of 240 times 7 for the height again, for the distance, sorry, plus the height, 240, which gives you 18.5 inches. God, sorry, I can't write inches for some reason. Inches, which is divided by 12, 1.5 feet. So let me just do a table just to summarise this. So it's 7 miles away. So it's for 0 inches, 72 inches, and 240 inches. So that's height. Obscured, 33 feet. 11 feet, 1.5 feet. So you can see how much is obscured by the curvature. The Earth drops very quickly as you move up, which is a fact that just, I don't know, it just seems a little bit lost on most people that are looking at this stuff. So anyway, that's my little tutorial on the mathematics of the sphere, just to help flat earthers out a little bit, because I've watched the floundering, and this is how you do the calculations properly. And this is a little, just to show you again, this is a little calculation formula here that I've worked out for you that tells you how to find how much of something the distance is obscured. When you put the distance in miles, the height of your eyes above sea level in inches, and this gives you the answer in inches. Okay, so this gives you the answer in inches. Right, hopefully you'll be able to make some better calculations from now on.